Thank you for attending the talk. My name is Kellian COTTART, and today I will present to you our new paper from Damien Keller's group at C2N University Paris-Saclay. So I'm glad to present this paper that has been accepted to Nature Communications about Bayesian continual learning and forgetting in neural networks. So I'm going to talk about something a bit different than what you guys did before. I'm going to talk about continual learning, and more specifically, real-time applications. Okay, so we've had plenty of new development on autonomous vehicle, healthcare, and IoT that received unbatched streams of data, often in unlimited supplies, because you keep on having new data from your sensors. And people have tried to track these uncertainties, more specifically Kendall, in what uncertainties do we need in Bayesian deep learning for computer vision. And safety critical contexts require these uncertainties because we need to trust the prediction that we're making. Okay, we need to know whether or not what we're going to hit with our car is someone or not, and if we have to adjust the model accordingly. We have to know what the model doesn't know, in fact. And this talk will be about how uncertainties can help with continual learning. So first I'm going to present a bit more about continual learning and the problem that we're facing, more specifically with catastrophic forgetting. And then I'm going to talk about another problem that we put in light, which is catastrophic remembering when you try fixing the first problem. Then I'm going to bring more information about what we did, so the paper that we published, about regulating these forgetting and remembering capabilities through metaplasticity from synaptic uncertainty. Oh, sorry, yeah, sure. And then I'm going to talk about the experimental results that we got from this new method that we've been developing. So let's talk about catastrophic forgetting first. Imagine that you have a binary classification task where you have to kind of decide, is this the animal that I'm looking for? Okay? You're going to be faced with several data sets. Let's take T data sets that have different animals linked with it. Okay? So a traditional neural network, if you're presenting it the first animal, which is a brown bear, progressively, if you train the neural network with new representation, it will overwrite the previous representation. Okay? And this is the problem of catastrophic forgetting. Deep neural networks are weak to evolving data, and we kind of forget all the previous representation that we've had before. Okay? So there are several methods to kind of circumvent this limitation. Rigorization, optimization, replay, representation, and architecture. I won't talk about them, but they exist. And today we're going to specifically talk about rigorization, and we're going to most specifically equip the weights of our neural network with a standard deviation to allow tracking uncertainty in each synapses. And linked with the talk that we've seen before, we're going to compute the aleatoric and epistemic uncertainty linked with it, and this will be the uncertainty measures that we have. So the aleatoric uncertainty is linked with the data. Okay, this is, okay, never mind. Is linked with the data, so the more data that we have, the more the prediction can actually fit this data, and the epistemic uncertainty, which stems from having different representation, different function that can match the data points that we have. So by conditioning the model on Bayesian statistics, we can express the degree of belief in an event and face lifelong learning. And we do this by computing the posterior distribution. So basically what we do is we have prior belief on the data, okay? What prior information do we have on the situation we're facing? And then a likelihood, that is how the new data set that I'm seeing will influence my model when I incorporate it, which give us the way we have to kind of update our probability distribution such that the information is implemented. And we can see here that we're writing every single information within this posterior, so from dataset 1 to T. What we do in practice is we don't compute this posterior distribution because it's a probability distribution, so we use Binfield Gaussian variational distribution instead. So we say that our neural network has every single weight equipped with a variance is a normal distribution, And with this set of parameters, we're able to use the callback-Labor divergence to bring closer the posterior from the mean field Gaussian and train the neural network with it. Okay, this has been demonstrated in Zeno's paper, Task-Agnostic Continual Learning using online versional Bayes. And they prove that neural networks are mitigating catastrophic forgetting using Bayes' rule. But the problem with this is that it gives an update rule like this, okay? So we have an update for our mean value parameter, which is basically the weight of your neural network, let's be fair with it, and an update rule for your standard deviation. And we call this metaplasticity because each synapse adjusts its own learning rate. So the variance of the system will condition how the system learns, okay? So here we can see that the learning rate that we usually see when we update through the cost function is in fact the uncertainty linked with the predictions, which means that the higher the variance, the larger the learning rate. So the more we're uncertain about data, the more we're going to need to learn about this data. And when we are very certain, then we're going to get closer and closer to zero, meaning that our weight will not move anymore, which means that our information is going to be retained because we're not going to update the neural network anymore. So Bayes' rule inherently brings metaplastic updates to neural networks. But the interesting thing is that when we apply this to the same situation that we've seen before, we're facing another problem, which is the more we learn, we can see that here we manage to learn both representation at the same time, but after some time we have the inability to learn that occurs. And this is what's called catastrophic remembering. Because basically what we did is we conditioned a finite model with finite set of parameters on infinite data. Because basically we can have, when t goes to infinity, we're going to bring more and more data and saying, okay, we remember all this data. So remembering all data sets prevents learning. And this is the opposite of what we want, because technically instead of, like I showed you before with autonomous vehicles, we're going to have a problem that, well, when you keep on learning information for an infinite amount of time, then you want to be able to adjust your belief according to this. We don't know what situation you're going to be in, and if you have no space anymore, then you're just going to be lost, and you're going to work with the model that you've had like for a while. So we need to find a way to fix this. So our research direction in our team is to know what triggers catastrophic remembering, how to maintain optimal discriminative capability through time, so meaning that the variance of the system will remain and we're going to keep on updating the system. And is it possible to avoid both catastrophic remembering and catastrophic forgetting? And this is what we do, okay? So we learn how to regulate it. Our hunch is that by considering a memory window of size n, corresponding to n data sets that we want to learn, we will be able to avoid this problem of catastrophic forgetting and avoid this problem of catastrophic remembering at the same time. Because forgetting happens when you don't let your neural network know about previous information. And the other happens when you let too much information into your system. So having a trade-off between both situations could be the way to solve this. And this is exactly what we do. So we have a memory window that will just slide, and information out of the memory window is gradually forgotten. How does this translate in Bayes' rule? Like this. So we're just going to update the posterior with respect to the memory window n, and we're going to say that we're going to write this law with respect to the data that we've forgotten before, which gives us this nice expression with learning in one part, which is exactly the same thing that we showed before, and a new term that is linked with forgetting. But we cannot compute this because, as I said, we're working with streams of data, and we don't have access to previous information. So we need to make an approximation with this. So what we're going to do is say that all data is weighted equally, okay? All data that we see in nature will be weighted equally to simplify the problem. It's not the case, okay? But it allows simplification, and we will consider that the prior distribution, that the posterior distribution and the likelihood are Gaussians, that we're only facing Gaussian data in the nature and everywhere. And this allows us to write this approximation that this probability distribution here linked with forgetting is simply like a power of what we need to compute here for forgetting, which is a normal distribution. Doing this we formalize learning and forgetting through a truncated posterior distribution, and we're able to compute exactly the same update rules as we've seen before, which gives us this new update rule right now, which differs slightly from FUBIB diagonal that we presented before for continual learning purely, because this one has the problem of going to 0 all the time. Okay, so the more you learn from your system, as you link your update rules with your variance, if you have no more uncertainty, you're going to converge towards 0. And it happens quickly because you always update this with respect to the variance. In our case, we don't, because we have a whole part that's dedicated to forgetting and to coming back to the prior distribution. And attuned readers will see that it's basically just rigorization. Okay, if you do L2 rigorization, you're going to have some kind of a magnitude that says you're going back to the state where you have maximum plasticity. But in this case, we link this with the variance of the system. So the higher the standard deviation, the more we're going to want them to go back to the prior. So we're going to basically compress the information by saying, okay, the least relevant informations are going to go back to the way they were before because they do not bring us anything. And the more information that we do not touch will also come back to the prior distribution. So what is Meso capable of doing? It's capable of preventing catastrophic remembering and rigidity by gradually forgetting information. Okay, so we don't lose the ability to learn. It conserves out-of-distribution detection ability through time by expressing high uncertainty. And we mitigate catastrophic forgetting within the memory window. So let's see some experimental results. First, I'm going to talk a bit about how we estimate uncertainties, which is something that we've seen before in previous talks, by simply stating that the epistemic is the mutual information, so the whole uncertainty of the model with respect to the data. And the aleatoric uncertainty, which is linked to the output given the model and the input data. Let's use a toy dataset first, which is the animal dataset, and let's make some tasks out of it. So here we can see that we have several tasks. First, we have 5 different classes: bears and related felines, ground birds, aerial birds, and grazing mammals, which are distinguished into 5 tasks. And the idea is to do domain incremental learning, meaning that I'm going to evolve the definition of a class through time. So here we have a red panda, here we have a polar bear, here we have a brown bear, and here we have a panda. So each task that we will see sequentially is going to have some kind of change with respect to the data distribution that we faced before. And we want to know whether or not we can remember this information and whether or not we're going to lose the ability to discriminate. And we're going to use whales as a way to assert that the out-of-distribution data is taken care of and that we can distinguish it from what we learn and what we haven't learned. So the interesting thing is when we train this with SGD, so stochastic gradient descent, we can see that catastrophic forgetting is happening. So here I'm plotting the epochs as a function of the test accuracy for each data set being in different colors. You can see that when we learn the first data set for 5 epochs, then we switch to a new data set, we're facing catastrophic forgetting. Okay, we do not remember what happened previously. And we can see that in terms of uncertainty detection, most of the data is very, very close together, so we are not able to distinguish what's in distribution and out of distribution. When we use Meso, we can see that we remember all subsequent tasks, and we do not forget about the previously seen information, while retaining high in-distribution and out-of-distribution detection abilities, because we're really able to make some kind of distinction between the distribution of what's out and the distribution of what's in. Okay. Now we're going to do some kind of a state-of-the-art to compare the different methods that we have. So first, let's talk about the rigorization methods that exist. So we have synaptic intelligence, which is a surrogate loss, basically, that we had through the model, which allows to compute the importance of each synapse. Okay, is my synapse important? Is the information relevant for this dataset specifically? And how does it work? And this is exactly what the update rule does. It says that, okay, basically you're going to heavily penalize the non-important synapses, and you're going to want to update them more frequently than very important synapses. Kind of the same with elastic weight consolidation, which has exactly the same system, but the importance metric is computed differently. And both these two methods require task boundaries to work, okay? Whereas the method that we presented before do not require task boundaries. What are task boundaries? It's that the algorithm knows ahead of time when the task changes and requires the previous parameters to work. So we need to compute another set of parameters that we faced before, and when we're facing streams of data, this is simply not doable. And then we have the two methods that we presented before. So let's check a permitted MNIST benchmark, which is a very traditional benchmark in continual learning. So basically we have MNIST, we permute each pixels for each class in a similar manner, so that the tasks are orthogonal with each other. And we do this 200 times, because 200 times will allow us to check for a long period of time. We input every single data in batch of 1, and we train this with a very small neural network, which has only 50 hidden neurons. And we compute this 10 times because we're doing Bayesian neural networks, so we need to compute several times the Gaussian distribution to have a reliable estimate of the prediction. So let's compare different methods together. So exactly the method that I presented before with SGD as a baseline that we added, and another method that we call EWC stream, which will be considering that the previous task is not the previous data set, but just the previous image that we saw, to kind of get a basis of what would happen if we were in a real context of learning through stream with these methods. And we can see here the test accuracy on the memory window for the last 5 tasks. The interesting thing here is that we see that the baseline performs very badly because it faces catastrophic forgetting. So we're forgetting every new data set that we're seeing because we haven't seen the information in a while. EWC stream works almost as good as SGD because the continual learning setup is not strong enough to hold with respect to the previous information. Okay, we're just seeing the previous image, so it's not enough to kind of track the importance of each parameter. And then the traditional continual learning methods work really well on this. Interestingly, we see that FuVB diagonal, which is the method that faces catastrophic remembering, performs really badly because we are not able to learn anymore. Hence, we're not able to compute the new task as we're doing 200 tasks. And it makes it perform very badly on this when it was supposed to be conceived to hold infinitely many data sets. And Mezu, by gradually forgetting information, is able to tackle this problem much more accurately. We devised another metric which is called the memory rigidity resilience, which is basically to know the difference between the accuracy we had in the first task and the accuracy we had in the last task, to see how much plasticity our network lost, okay? Are we able to learn the last task as well as we learned the first task when we didn't know anything about the data? And interestingly, we see that even methods like SGD are not able to learn as correctly as before because the magnitude of the weight increases through time, through tasks also. And FuVB diagonal is the one that performs the worst because of the memory rigidity and the loss of ability of learning. Whereas Mezu is able to retain its full capacity and to learn as well as it did on the first task. Finally, we can assert out of the distribution data detection. So here we're going to identify fashion MNIST in front of permitted MNIST, and we're going to see how well the different models perform. So all different methods perform pretty well on this, I would say. And the important part is that whenever you face the inability to learn, you also lose all discriminative capacities here. So the only way to recover this capacity is to avoid having your variance going to 0, hence why Mesu performs better than all other methods, because it always tracks the uncertainty and always avoids this uncertainty to go to 0. So this is just a summary of what we've just seen, and we can state that Mesu is resilient against the loss of plasticity even after more than 200 tasks. So it's well adapted in a continual learning setup and in a lifelong setup. And this method does not require task boundaries to perform well, which is a great improvement over all other methods that were presented. Let's check a more complex experiment on Cypher 10 and Cypher 100 to see if it works well with convolutional neural networks. And here we're going to train the neural network on Cypher 10 first, and then add 10 classes per task. So we're going to do task incremental learning. So our architecture will be, the architecture of the classifier at the end will be 512 and 10 plus 10 neurons per task. So we're going to add 10 neurons each time we face a new task. And only when we're evaluating the dataset, we're going only to look at the 10 tasks that were used for this specific task. Okay, so it's some kind of masking. So whenever I'm facing, I don't know, I'm doing task 2, so I'm going to compute only neurons from 11 to 19. Okay, 11 to 20, sorry. So here, what is our methodology for this? We are taking each individual task and subdividing into 1, 2, 4, 8, and 16 splits, and then we interleave all the splits. What this does effectively is that when we have only one split, we're going to see all tasks sequentially, so it's going to be a very easy setup for continual learning. Like all continual learning methods will be advantaged over this. Whereas when we interleave a lot, it's going to be very good for non-continual learning methods because we're going to see the data over all tasks over and over again much more frequently. Okay? And this is to assert that Mesu really performs better than in all this kind of situation, thanks to the memory window. So let's go. Here we're going to take a look at the number of splits and the test accuracy on whole different tasks, like the mean test accuracy on 11 tasks. And we can see that no matter the number of splits that we're doing, so either we're very favorable for continual learning methods, as we can see with EWC and SI being on top and ADAM being below, we're performing better than all other methods. And at the end, even with 16 splits, where it's supposed to be very, very comfortable for ADAM because we're seeing the information over and over again, Mesu still outperforms this. And we have like the details of this graph per task, and we can see that we're pretty much above all the time with Mesu, showing that the Bayesian way of doing things outperforms even standard algorithms on tasks that are more easy for them and still retains optimal capabilities for continual learning. Yes. So thank you for listening. I will take all your questions if you have, and thank you for attending.
Thank you a lot for your talk. Other questions in the room? Okay.
Great talk. I'm very surprised that the variational inference Bayesian neural networks work so well, because in literature they seem to have a lot of problems, like posterior collapse. Would you say that this is a way to make it not collapse, the posterior?
I would say that we do it very differently than what's usually done in the literature. Because what we can see in literature with the variational Bayes inference is that we're computing a surrogate loss based on like the traditional loss of neural networks plus the computation of the KL divergence with respect to like the posterior distribution and the current distribution. But we're doing this within the loss. So we don't have really, we don't state what the posterior should look like. We don't make any approximation of the posterior, and we don't make any approximation on the prior. We usually do different priors and we see how the priors behave. Here, as we're doing always the normal distribution approximation, we have a closed form for the updates, which makes it behave very differently. Like we can just update our parameters without caring so much about whether the posterior is going to collapse or not.
Okay, so this makes it more stable in a way.
I would say so, yeah.
That's interesting. And then my other question was, so this is very typical, I would say, high quality machine learning research.
Thank you.
But what annoys me with this is just that all your validation, it's on these images.
Yes.
Have you considered doing any validation on non-image data? So data which is more, I guess, interesting to us as physicists.
Yes, of course, we've thought about that, but this is not the main focus of the paper. Like, I solely presented the experimental results here for the sake of clarity, but our work is very much on how to derive the algorithm, how to formalize this Bayesian transformation, and how to bring it forth, like we do differential equation to state how it behaves in infinite states. So it's more mathematically focused, I would say, than physically focused.
So
but
someone else can do the validation,
yeah.
I guess. Yeah, that would be just cool to see on more mathematical test distributions.
Yes. And this is what we're aiming for, basically. What we want to do is to implement this kind of algorithms into electronic devices. So we would need actually real kind of situation that would require validation like this, and to see if we stem uncertainty from this. So this is actually my work. So this was my first work of my PhD. And now I'm conducting work on binary, like doing everything like this, but on binary distributions, so Bernoulli distributions.
Yeah.
And to see how with bytes we can actually manage to get to more complex setups.
It's super cool. I hope it goes well.
Thank you very much.
Super interesting. Yeah.
Thank you. Yeah, thank you for the great talk. It's a very good paper. I work in object detection and data fusion for autonomous vehicle.
Okay.
And I'm very curious about the feedback you got from the reviewers about the normal or Gaussian distribution hypothesis on your data, because I submitted this paper to CVPR, and my hypothesis was that all the data is Gaussian, and I got really bad reviews just about it. So what was the feedback?
Okay, so we do not really suppose that all data is Gaussian, but like the likelihood of observing data is Gaussian, which is a bit different. Okay, so we do not make any assumption about data, just about its probability distribution. And the reviewer did not make any feedback about this. They were more interested in how the different n's, because there's an hyperparameter n, that is the number of data sets that we can learn with Mesu, how this behaves, like how the system behaves when faced with different values of n, and how it evolves through time and so on. So this was more a review questions.
Okay, thank you.
Welcome.
If not, I might have one on more on a memory retaining task. So you showed metrics on how well the models actually behave on the last 5-6 tasks.
Yes.
So the question is actually twofold. First, you probably showed it, but I almost surely missed it. Can you control the sliding window, the width of the sliding window of the forgetting?
Yes.
And consequently, what's the performance on the last tasks, but in the very first part of your window?
Mm-hmm.
So not the very last, but less. Okay.
Very interesting question. Thank you for asking. So here is the graph on task number. So we have the number of tasks that we're facing. Here we have the test accuracy at the end of training on each task. And here we have different memory windows. So n equals 180 corresponds roughly to 3 tasks. Here we have 5 tasks, here we have 10 tasks, 20 tasks, 30 tasks, and then infinite number of tasks. And we can see that by enlarging the window, we will lose plasticity through this, but we will retain more information. So this is the first part of your question, I think. And the second part of your question is, here you can see that the accuracy is gradually released through time. So we go back to basically random guesses after some time. So the first task would be at 10%, so random guess.
Okay, thanks.
Thanks for the talk. This is maybe more of a high-level question. I'm
Sure.
not very familiar with the literature in this field, but I'm wondering, like you had this stochastic gradient descent baseline, and then your method outperformed it in a lot of different tasks. And I'm wondering how much more computationally demanding is your task, and like would scaling up the network used for SGD, like if you scaled it up to the same computational complexity of your method, or is your method like almost equivalent to SGD?
So what happens here is that we're doing, as I said before, we're Bayesian, so we have a distribution, so we have to sample multiple times, so you're right for asking about complexity. So what happens is that we're doing 10 samples here, but we do not have to do 10 samples. We're going a bit overboard with this. So we can also bring ourselves back to 3 to 5 samples, which would still make it like 5 times more, actually 10 times more computationally intensive than SGD, because we have one parameter for the mean, one parameter for the variance, and then we do this multiple times. But if you're talking about hardware specifics, I don't know if this would be.
You said that it's still 5 times. Would it be like if you scale up the network for SGD like
Okay.
5 times? Would like it would be interesting to see if your method still is, because of like how you structured the compute, like that it would be better, or if like just scaling up the compute of the normal neural network also would make the continual learning better.
In terms of number of parameters, you mean?
Yeah, I mean in general the amount of flops that both methods use.
Then I would say that the Bayesian method is always more computationally expensive, but the idea of like so SGD would perform way better in terms of efficiency for this.
But I mean, like, let's say you have your method that samples, for example, 10 times and uses Bayesian neural networks, and then the baseline with SGD, you scale that up exactly so that it matches the amount of flops.
Yes.
Of the first one. It would be interesting to see if the continual learning.
Okay, so I understand the question. SGD always faces catastrophic forgetting no matter what size of the network it is. Okay. So you're always not going to have good performances on continual learning with SGD. It's not going to retain more information because of the size. It's just a representation problem. And the more you overfit your data, the more you're going to face catastrophic forgetting because you're going to have this problem occurring. So it's more a matter of what happens in the neural network than what happens in the update rules rather than really how you scale your neural network.
Okay, so just scaling up would not solve this.
Yes.
Okay.
Yes.
Thank you.
And the interesting thing is that in a real life setup, you would have only one network and you would sample multiple times, like you would do multiple inferences. So it wouldn't require to scale up the neural network that much. Okay. So it would be twice, like the number of parameters would still be twice as much as SGD, but you wouldn't have to, like the sampling comes naturally. So,
okay.
So that's the trade-off about it.
Thank you.
I think it's too far away to be workplace safe. So.
Yeah, so thank you for the very good talk. I had a question regarding the task window that you were using. So you were using a just sliding task window where you remember n task, but have you considered or tried or give any hints about just also conserving n task, but not in a window that could be sliding, but like trying to remember which data set you have seen contain the more critical information and just remember these ones in order to be sure not to lose critical information by forgetting about them with the sliding window.
Very interesting question. So you mean like pinpointing specific data sets that would require?
Yeah.
Yes. So in fact, it is a bit what the neural network does on its own, because if you train a lot on data, you're going to have a variance that goes almost to 0, and the only determining factor for losing this information, okay, this very important information that you're mentioning about, will be to go towards infinity, okay? So you will still retain what's very important at this moment because your synapse is going to be very much consolidated, and so the releasing of the information will only act with respect to how consolidated the synapses are. So if you make so that the data set is more important than others, you will retain it more like longer than others. Yes, and we've tried this. Yes.
Okay, thank you.
More questions? If not, we can thank the speaker.